In this video, we use the alternating series test, the ratio test, and the root test to determine whether an infinite series converges. If you like this video, don't forget to like, subscribe to the channel, and activate the bell. It is very important for the continuity of this channel. An alternating series is a series whose terms of the summation alternate between positive and negative values. Here are two examples. An alternating series can be defined as follows. Let A sub n be a positive sequence. An alternating series is a series of either the form. We now state a powerful convergence theorem for alternating series that meet a few conditions. Let A sub n be a positive decreasing sequence. If the limit of the sequence is zero, then the alternating series converges. Let's prove this theorem. The basic idea behind this theorem is illustrated in figure below. A positive decreasing sequence, A sub n, is shown along with the partial sums. First, note that because the terms of the sequence are decreasing for any two successive terms, we can say. Now, let's take a look at the even partial sums. We can see that the even partial sums are increasing. We can rewrite the even partial sums as follows. And we can see that every term in brackets is positive. So this partial sum is less than or equal to the first term. Therefore, the sequence of even partial sums is increasing and bounded above. It is therefore convergent by the monotonic sequence theorem. Let L be its limit. Now, let's take a look at the odd partial sums. Now we compute the limit of the odd partial sums. The two sequences of partial sums converge to the same limit, and this means the entire sequence of partial sums also converges to L. Since both the even and odd partial sums converge to L, the series is convergent. Let's see how it works. Determine if the series converges or diverges. When we use the alternating series test, we need to make sure that we separate the underlying sequence from the part that makes it alternating. The underlying sequence A sub n is positive. We now check whether it is decreasing. We can do that by replacing n with n plus 1. We can see that the left side is bigger than the right side because the denominator on the right side is bigger. Hence, the term is actually smaller. So we just concluded that the sequence is decreasing. Finally, we compute the limit of the sequence. Since the underlying sequence is positive decreasing and has a limit of 0 as n heads towards infinity, the series is convergent by the alternating series test. Be careful to note that the test can only confirm that a series converges, but cannot be used to tell us that a series diverges. So here is a tip to you avoid unnecessary computation. If you see the alternating series, first check the divergence test. If this test holds, then the series diverges, and it's the end of the story. If not, then apply the alternating series test to check the convergence. Let's solve item B. First, we separate the underlying sequence from the part that makes the series alternate. We now check the divergence test. Since this limit is not zero, then the series diverges, and it's the end of the story. Let's solve item C. First, we separate the underlying sequence from the part that makes the series alternate. We now check the divergence test. Since this limit is zero, then we apply the alternating series test to check the convergence. Next, we check whether or not the sequence is decreasing. We take the derivative of this function. We see that this function is decreasing for all n greater than 2. Hence, by the alternating series test, the series converges. Let's learn about the ratio test. This test is particularly useful for series involving factorials and exponentials. This theorem states that let A sub n be a positive sequence for which the limit of the ratio of their successive terms is L. If that limit is less than 1, the series converges. If that limit is greater than 1, or if that limit does not exist, it diverges. And if the limit is just 1, we do not know. It might converge, it might diverge. We will use the comparison test to prove the ratio test formula, and we'll break the proof into two parts. 1. When L is less than 1, the series converges. And 2. When L is greater than 1, the series diverges. The goal is for us to compare the given series with a convergent geometric series. The idea is to compare the given series with a convergent geometric series. Since the absolute value of the ratio of consecutive terms converges to L, there exists a number m such that the absolute value of the ratio of consecutive terms converges to R for all n greater than or equal to m. Therefore, we can rewrite the inequality as shown below. Putting successively equal to n, n plus 1, n plus 2, we get the geometric series on the right converges, and so, by the direct comparison test, the series also converges. Recall that a finite number of terms does not affect convergence. Now let's work on the second case. The proof is similar. If L is greater than 1, we work as before with the inequalities reversed. And we find the geometric series on the right diverges. And so, by the direct comparison test, the series also diverges. Part C is left as an exercise. To solve item D, we first take note of the expressions of the sequence A sub n and its consecutive term. Second, we find the absolute value of their ratio. Third, we take the limit of the resulting expression by evaluating the limit when n approaches infinite. Because the limit is less than 1, The series converges. To solve item E, we work as before. We first take note of the expressions of the sequence a sub n and its consecutive term. Second, we find the absolute value of their ratio. Third, we take the limit of the resulting expression by evaluating the limit when n approaches infinite. Because the limit is greater than 1, the series diverges. Item F shows that if the limit equals 1, the ratio test is inconclusive. The first series, we know it is a convergent series. In the second series, we know it is a divergent series. As we can see, the ratio test for both is inconclusive. So, when the ratio test is inconclusive, to determine whether the series converges, you need to try a different test. The next test is known as the root test. As its name suggests, it involves taking a root, and so it is most useful for exponential series and in situations where taking a root is quick and simple. This theorem states that let a sub n be a positive sequence for which the limit of the nth root of the absolute value of the sequence is all. If that limit is less than 1, the series converges. If that limit is greater than 1 or if that limit does not exist, it diverges. And if the limit is just 1, we do not know. It might converge. It might diverge. Its proof is similar to the proof of the ratio test. I'm not going to do it here, so this video doesn't get too long. You can find the proof in a calculus textbook. Let's see how it works. To solve item G, we identify the sequence and we can directly apply the root test. As this limit is less than 1, the series is convergent. To solve item H, we identify the sequence and we can directly apply the root test. As this limit is greater than 1, the series is divergent. To solve item I, we identify the sequence and we can directly apply the root test. As this limit is 1, the test is inconclusive. We should apply another test to verify whether this series converges or not.